Today we're going to get more into the physics and quantum model of the atom. So this is academic chemistry, chapter 5, section 3, part 2. Today we're going to specifically talk about energy of photons. Now remember, photons are little packets of light, and they travel through the universe in these little wave things. And they're kind of like a particle because we can track them, so that makes them like a particle, but they're like a wave because they literally move like a wave. So photons only absorb a discrete amount of energy, and that's called a quantum of energy. And what discrete means is a certain piece of energy. So it can't absorb any amount of energy. It has to be specific amounts called packets or quantum of energy. Now, if you look at this chart, you can see that this energy is being absorbed, like you get this bit, and then you have to absorb a certain amount more, a quantum more, and then a quantum more, and a quantum more. So these photons only absorb certain amounts of energy. So it would be like if you could only get $10 a week in allowance, and like your parents weren't allowed to give you $1 or $5. They had to give you $10 or no dollars. That would be a quantum amount or a discrete amount of money if you always got bits of $10. You couldn't spend $8 or $12. You had to spend everything in $10. You had to receive everything in $10 increments. Now, it's hard to imagine this because photons absorb these little teeny tiny bits of energy. So look what happens as this chart becomes smaller. That discrete line eventually looks like a straight line. So those jagged edges look straight. So that's why we don't really think of it as specific amounts. We think of it just absorbing energy and energy, but it is only absorbing certain amounts of energy, these little packets of energy. Atoms absorb discrete amounts of energy based on what kind of element it is. So here you can see those different energy levels that we had before, energy level 1, 2, 3, 4, 5, 6, 7, as you go further away from the nucleus. There's certain amounts of energy that it takes to get from here to here, or from here to even up here. And that's a specific amount, and it depends on the electron configuration. So energy transitions occur in jumps of discrete amounts of energy. Electrons only lose energy when they go from to a lower energy state. So they were in an excited state and they went to a ground state. So what do I mean by that? So here's the atom and it's just hanging out and it's in ground state, which is what you've done for your electron configuration. So fill in the lowest energy possible. Think about like someone who's grounded is very low energy. So the electron's hanging out here in the first energy level, and then it's going to absorb some energy. So that's called the absorption spectrum. Atoms only absorb a certain amount of energy within whatever their spectrum says they're going to. So now our electron is in the excited state. So this electron is supposed to be here in the first energy level. It's now hanging out here in the third energy level. It is in the excited state. It has more energy. It's like, what? Going far away from the nucleus. Oh my God, this is crazy. But eventually the electron's like, I'm chill. I don't want to have this high energy state anymore. I got to get this energy out. Like, I don't want it anymore. So the electron goes back down to where it started, and that's how energy is released from atoms in the emission spectrum. Okay, so you remember that the electromagnetic spectrum is all those different types of electromagnetic radiation. Gamma rays, radio waves, infrared waves, all of those are packets of energy that are traveling through space. Out of all of those things, this little itty bitty bit is actually light that we see. We see a very small amount of electromagnetic radiation. Now, when you have something like the sun, you'll have a continuous spectrum of light. You release all of these types of light. But if you heat up elements, elements only release certain types of light. So if you take a gas, that's what you're going to be doing in your next lab. If you take a gas and you heat it up, you give it a heat source. So before we did metals, so not a gas, and we put them in the fire, and that's how we saw the color come out. Now you're going to have a pure source and just put an electric current through it. And whatever it absorbs from the continuous spectrum, that's its absorption spectrum. And then it's going to release the same stuff, but that's the emission spectrum. So light from the sun creates a continuous spectrum or a rainbow, and that's what you see in the sky, right? When it is sunny and wet out, because all those droplets from the rain act like little prisms, so they break up the light into its spectrum or rainbow. but atoms only emit certain wavelengths and frequencies of colors that we see. Light is given off by these excited atoms as they return to the lower energy states. So remember, those atoms absorbed certain amounts of energy, and then they release the exact same amounts back out. Now, it's not every single type of color or EM spectrum, right? So maybe an atom only releases yellow and green, right? But another guy might release yellow, purple, and red. It all depends on what type of atom, because it absorbs based on its electron configuration. Like, it can jump certain amounts based on where the electrons were and where they can go. So we're going to use a spectroscope in your next lab, and that's just a device that has a little prism in it, so it can reveal the lines, the particular colors that pass through that prism, where you can see the specific frequencies off. You see, when we see, as a human eye, if we see a bunch of different colors coming together, our brain automatically pushes them together and makes one color that came from multiple light sources. But what a prism does is it breaks apart those lights so we see them. It slows some of them down so that way we can see them on different pieces. It breaks them up and says, oh, you go over here and you go over there. So our eyes can see different types of light as opposed to all those colors smushing together and making one color. That's what we saw in the flame test. We saw one color because there was no prism. So our brain just processed all of it together. But in the next lab you have, you're going to break it up and you're going to see all the different lights in the spectroscope. All right, each element has a specific fingerprint of its atomic spectrum that it releases. So beryllium, for example, has these wavelengths, right? It has something about 385, it's got something about 410-ish, okay? These are in nanometers, by the way. So if this is our unknown, what element is it from what we can see? Well, it can't be beryllium because beryllium has a purpley line that comes out of it, okay? Even though these match up and that's close, it doesn't matter. Beryllium also has this green line that our unknown doesn't have, so it can't be. Can't be copper. Copper has all these yellows that our unknown doesn't have. It can't be manganese. Manganese has that purple and, you know, none of these reds. Strontium has the bluish, dark bluish indigo, some blues, an orange, a red. Oh, look at that. Looks pretty similar. Can't be titanium. So you know that the unknown is strontium. Atomic emissions is how we can see what's way out in space, super, super, super far away. So atomic emissions can be used to identify elements over great distances, like stars. Stars have all this compact gas, and then so we can see it, and we can break it up through a spectroscope in a very large way, and we can actually identify which elements are in stars millions of years away from us. A lot of times what's super cool about this is when we look at these stars, the stars are actually dead by the time the light gets to us. That's how far away they are. These stars are no longer in existence, but the light that they've released continues to travel and come to the Earth as we can see it, and we can say, wow, millions of years ago when that star was alive, not like biologically alive, but active, it had helium, it had nitrogen, it had some lithium, probably not, but yeah. And that's how we can tell what's so far away without ever sampling the stars, which is really cool. So today you're kind of going to do that, but up close and personal with the Atomic Emissions Lab. Okay, good luck.